Okay, so I am assuming that everybody has gone back and reviewed lecture 10, 9, 10, 11 for this lecture because we are going to talk about Jordan canonical form today. Okay, so recap. Uh, oof. So I bruised my finger, so my handwriting is going to be slightly off, but I am actually Abhishek. I'm not an AI avatar of Abhishek. So uh, just by looking at an handwriting, do not. Oh, so this is my linear system for today's discussion. It's a discrete time linear system. So in the previous lecture, we said we are tired of continuous time linear systems. We don't want to study continuous time linear systems ever again. And we want to just stay in the discrete time domain because we are living in 2026 and everything is computer controlled. Um, so this is my discrete time model. And in the previous lecture, we also discussed how to get this A matrix for the discrete time using the A matrix for the continuous time. Now today, towards the end of the lecture, we talked about the modes of the system. So in the case A was diagonalizable, so I have A t equals to t lambda. This means A equals to t lambda t inverse, and t comprised of all the eigenvectors of A. So I'm assuming that there are distinct eigenvectors of A, therefore you can have n distinct eigenvectors of A. They are linearly independent. So this whole operation is feasible, and in which case A is diagonalizable. So when A is diagonalizable, I don't know who comes up with these long terms. So when A is diagonalizable, then A equals to T lambda T inverse, and lambda is diagonal. And as you can imagine, lambda contains all the eigenvalues of A matrix along the diagonal. And I can write actually lambda can be written as summation lambda I EI transpose I equals 1 to n. So EI transpose is a diagonal matrix where you have 1 at the ith diagonal entry and 0 everywhere else. So this means that A can be written as summation I equals 1 to n lambda I T EI transpose P inverse. And in fact, A raised to k can be written as lambda I raised to k. So this was the modes of the system. I had n modes of the system. And we stopped our discussion in the previous lecture at this particular point. So this is all recap from the previous lecture. We were looking at the case when A is diagonalizable. I can use the eigenvectors of A to construct the matrix T. I can do T lambda T inverse. I get a diagonal matrix lambda. I can write lambda in this particular fashion. And so if I'm doing a raised to k, it's t lambda raised to k t inverse. And so I can expand this whole summation and it looks like this. So lambda I is getting raised to k, and that tells me what the mode of the system is. The other thing we discussed in the previous class was that if lambda I is less than 1, so the absolute value of this complex number lambda I is less than 1, then lambda I raised to k goes to 0 as k goes to infinity. So it becomes a stable mode. So the mode is stable if the absolute value of lambda I is less than 1. So if lambda I is a plus jb, then absolute value of lambda I is equal to square root a square plus b square. I want to connect this discussion to the discussion in the continuous time system. So if you recall, in the continuous time case, we said that the modes are stable if the real part of the eigenvalue is negative. So how does real part of the eigenvalue being negative for continuous time system translates into absolute value of eigenvalue being less than 1 in the discrete time system? So let's look into that. That's a divergence. The reason why I'm doing this divergence is because I want you to understand that the two systems are not independent, they are all connected through this matrix exponential. So if you recall, so this is a digression. I will get back into the case where A is not diagonalizable, so we have Jordan canonical form, but let's go through this digression first. So remember, my AD was e raised to AC times t. T was the sampling time, AC is the A matrix for the continuous time system, and AD is the matrix for the discrete time system. I can do this whole, so let's say T lambda T inverse equals to AC. We know from our theory, I think back from lecture 8 or 9, when we talked about matrix exponential. Oh, I know what the problem is. This T is sampling time. Okay, TS. Let me use TS. So this TS is sampling time. This T is the eigenvectors of AC matrix. Okay, I hope you will understand the difference between these. In the previous lecture, I had used capital T for sampling time, but now I'm changing it to TS. Okay. So from matrix exponential, T inverse e raised to ACTS T equals to e raised to lambda TS. I can equivalently write it as e raised to ACTS equals to T inverse, no, T times e raised to lambda TS T inverse. So I'm going to assume that everything is diagonalizable. So what I have is AD equals to e raised to ACTS equals to summation e raised to lambda I t t ei ei transpose t inverse I equals 1 to n. Anything that you notice? Oh, this should be ts. Oh, this lambda I is eigenvalue, so lambda I here eigenvalue of AC. How about I use lambda IC? So I know that lambda I is the eigenvalue of the continuous time system. Anything you notice between this expression and the expression here? So what I'm seeing here is that this lambda ID, the lambda I of the discrete time system, is e raised to lambda IC times Ts. So my lambda ID is e raised to lambda IC Ts. Okay, so this is the first insight that we got by looking at discretization of the continuous time system. It's a linear system. I'm discretizing the continuous time system. I'm doing the sampling. And what I have done right now is connected the eigenvalues of the discrete time matrix with the eigenvalues of the continuous time matrix, and the sampling time actually influences the strength of that connection. We said in several lectures ago that the continuous time system is stable if the real part of this eigenvalue is negative. Okay, and you've done a bunch of assignments where you showed that in the battery pack or in many other situations, in the case of aircraft, if your eigenvalues have negative real part, then system is stable, things will die down. Otherwise, system is unstable and the state will go to infinity. Wonderful. So how does that affect the absolute value of the eigenvalue of lambda ID? So let's look into this. So let's say my lambda IC is A C plus J BC. So J is negative minus 1. And let's say this is negative. I want my real part of the lambda IC to be negative. So what is the absolute value of lambda ID? It's e raised to, absolute value of e raised to minus AC plus JBC time TS. Can someone tell me what this value looks like? So all the complex number ninjas in the class, what is the absolute value of this expression? Any thoughts? Sorry? The same? It's not the same. T is always positive, for sure. TS is always positive. So E is always positive. E is always positive. But there is a square root of -1 here. Okay, the square root of -1 here. So it's a complex number. Okay, so this is actually equal to e raised to negative AC TS. So what is e raised to negative ACTS? What's the value of this? This is always less than 1. Because I assume that AC is positive, the real part of lambda AC is negative positive number. So it's a negative number. So I have a negative number multiplied by TS. I'm taking that as the exponent of an exponential function. And whenever you do exponential of negative number, it's always less than 1. So the stability criterion that I have here is the same as what you would get in case you had negative real part in your continuous time system. So in fact, your discrete time system is actually supposed to closely mimic the evolution of the continuous time system, and that's what you are seeing, that the two ideas are very, very connected. Negative real part of the eigenvalues of continuous time system leads to less than 1 amplitude of the eigenvalues of the discrete time system. Okay, so this is the connection. I know that many people use this connection without necessarily understanding. I myself didn't understand this connection for a long time when I was a graduate student, but now you know. That's how you go from continuous to discrete, and that's how the ideas from continuous translates to discrete, and from discrete it translates to continuous. It doesn't matter what the sampling time is, by the way. So whether you are sampling at 50 milliseconds or 500 milliseconds or 5000 seconds, it doesn't matter what the sampling time is, because you have a negative exponent here. The absolute value of lambda ID will always be less than 1. Okay, any questions so far on this topic before I jump on to the Jordan form? Okay. So if you're doing robotics, or if you're doing autonomous vehicle, or you're doing engine design or battery design, somebody's saying let's do continuous time system, somebody's saying let's do discrete time analysis. The fact is you will get to the same result no matter what analysis you do. Okay, now I'm going to look at case 2. A is diagonalizable. Sorry, A is not diagonalizable. And then my lambda is in the Jordan canonical form. You've done a few assignments with the Jordan form, so you kind of understand what this Jordan form means. T here comprises of all the generalized eigenvectors of the matrix A. So you stack all the generalized eigenvectors of the matrix A as columns of T, and that's how you get this Jordan form. Now the question is, what are the modes of the system in the case of Jordan form? So I'm not going to go through the most general setting. Let's just assume that I have a single eigenvalue lambda and I have a Jordan block of size n. So my lambda looks like lambda, 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 1, 1, and then 0 everywhere else. So I have the same eigenvalue but repeated n times, and I have a Jordan block of length n, something like this. And I want to start with some examples. So let's say I'm going to take eigenvalue 0.5, 1, 0, 0.5. So this is already in the Jordan form. And let's say my x0 was equal to y1 and y2. Not equal to 0. So I have something that's not equal to 0. What do you think is going to happen as k goes to infinity? So I start with a non-zero initial condition. I have this Jordan form. My eigenvalues are 0.5 and 0.5. This is a Jordan block of order 2. And the question is the state going to blow up or is the state going to go to 0? Okay, let's see. What is x1? That 0.5 y1 plus y2, 0.5 y2. What about x2? 0.5 square y1 plus 0.5 y2 plus 0.5 y2, 0.5 square y2. Did I do this right? Okay, so I can simplify this. I can write it as 0.5 square y1 plus 2 times 0.5 y2, 0.5 square y2. What about x3? Two. I can write it as pattern. I want you guys to recognize the pattern. What kind of pattern are we seeing in this iteration? What does xk look like in this case? Xk is, anybody wants to tell me what the pattern looks like? Right, lambda raised to k. Yeah, perfect. Awesome. This is the pattern. This pattern goes to 0 or this pattern goes to infinity? What do you think? It should converge to 0? Right. So lambda raised to k is going to 0 for sure, but there is one term here that's blowing up to infinity and the other term that's going to 0. K goes to infinity, lambda raised to k minus 1 goes to 0. And this term goes to 0. So this term will go to 0, this term will go to 0. What about this term? What do you think? What happens when you multiply something that's going to infinity with something that's going to 0? 0? Anyone else has any thoughts?
Depends which one's faster.
Sorry?
Depends which one's faster.
Which one is faster? So which one is faster in this case? Exponent, right? So exponent is always faster. This one is faster. So this is going to 0 faster and this is going to infinity. So it turns out that k times lambda raised to k minus 1, this term will also go to 0 because this is going to infinity much, much slower than lambda raised to k going to 0 is. So this system is stable because you start from any initial condition. Eventually the system state is going to converge to 0. Wonderful. Now let's change this to I'm going to make it 1111, 1101. Okay, so now my eigenvalues have changed. It has become okay. Let's see. I'm going to erase all of this. So xk here lambda raised to k y1 plus y2 y2. So when eigenvalues were 0.5, this converged to 0. Now my eigenvalue is equal to 1. What is xk? What does xk look like? In this case, it's y1 plus k times y2 and then y2. Is this going to 0 or going to infinity, or what is it? Where is it going to? What do you think? Infinity, right? So if y2 is non-zero, then this is going to infinity or minus infinity depending on the sign of y2. But because this one is growing to infinity, this one remains constant, this one remains a constant. But this term, depending on if it is 0, then it's stable. If it is non-zero, then it's going to go to infinity. Okay, awesome. So it seems to me that if your eigenvalue is equal to 1 in the Jordan block, then it is a problem. It was not quite a problem here, by the way. In the case where A was diagonalizable, so each eigenvalue 1 had its distinct eigenvector, which is linearly independent of all other eigenvectors. in that case, it will not blow up. But if you have a Jordan block, then it's going to blow up. If you don't have distinct eigenvectors, then you have to go to generalized eigenvector, in which case this is going to be unstable. It's going to go to infinity. So let's see what so now the question is, what are the modes of the system? So I think by looking at this expression, you can actually try and figure out what the modes of the system are going to look like. So there will be some modes with lambda raised to k term, as is the case here. But you will have some mode which is k times lambda raised to k minus 1. Okay, so that's the new term that will emerge in the context of non-diagonalizable A matrix. So let's do the analysis. So I can write my A matrix as lambda. No, A is T lambda. Okay, I'll write my lambda matrix lambda I plus n. Everyone remembers this n matrix? N is like 1, 1, 1 along the off diagonal term. We use this matrix even in the continuous time case. One thing that we had mentioned is that identity matrix and n commute. Okay. Let me remind you, n is 0, 0, 0, 0, 1, 1, 1, 0, 0. This is what the n matrix looks like. So it has 1 along the upper half diagonal entry, above diagonal entry, and then 0 everywhere else. That's my matrix n. Okay, so what does my A raised to k? So I need to have this sort of decomposition for A raised to k. And in order to do the decomposition, I have to figure out what lambda raised to k looks like. So A raised to k equals to T lambda raised to k T inverse. Now what is lambda raised to k? That's lambda I plus n raised to k. What the hell is lambda I plus n raised to k? What is this? How do I expand this? So this is the typical thing. K choose 0, lambda raised to n, identity raised to n raised to 0, plus k choose 1, lambda raised to n minus 1. I'm not going to write identity, but it's going to have n raised to 1. K choose k n raised to k. Lambda raised to 0. Let me write lambda raised to 0 n raised to k. Oh, did I mess it up? I did mess it up. This should be k, not, yeah, this is fine. Lambda raised to k, n raised to 0, lambda raised to k minus 1, n raised to 1, lambda raised to 0, n raised to k. Yeah, okay, this looks correct. What is k choose 0? This one is equal to k. This term will be equals to k square, k times and so on. Any questions so far? So let's go back to the train of thought. I have a matrix A, it's not diagonalizable. I constructed the matrix T using the generalized eigenvectors. I get lambda in the Jordan form. I can write lambda as lambda I plus n. Lambda is the eigenvalue. N is this matrix which has 1 in the off diagonal entry. And then I can write a raised to k. So I know that T is an invertible matrix. So I can write a raised to k as T lambda raised to k T inverse. I want to find the modes of the system. So I want to find what this lambda raised to k looks like. I did this expansion. What is this expansion called? I think binomial expansion. I don't know what it's called. A plus b raised to k. I think it's called binomial expansion. So I did this binomial expansion for matrices, and because I and n commute, this binomial expansion is actually extremely easy to write. The only reason why I can write it in this way is because it's I and n, these two matrices are commuting with each other. So I can write it in a simplified format like this. Then I can write my a raised to k as summation j equals 1 to. The other thing to note is that n raised to n is 0. So I want to add a remark here before I go to a raised to k. I think in lecture 10, no, maybe 9, I don't know. Lecture 8 or 9, we had proved that n raised to n is a 0 matrix. Because as you multiply, so n square has elements, these ones are essentially shifting towards the corner in the n square, n raised to 3, n raised to 4, and so on. So n raised to n, it basically becomes identically 0. So most of the terms in this binomial expansion is going to get killed after a certain value of n. So n raised to n onwards, everything else will get killed. So what I will have is a raised to k, and this expression differs from what's there in the book, is going to be equal to summation j equals, no, not j. Let me write I equals 0 to n minus 1, k choose I, lambda raised to k minus I, n raised to I. T n raised to I T inverse. These are the modes of the system. Okay, this expression differs slightly from the book. So the book says k choose I. This is what the book says, k choose I. You can think of it for k very, very large. It almost behaves like k raised to I minus 1. Almost, when k is very, very large. So the book notes it down as k raised to I minus 1, lambda raised to k minus I. It's fine. Both of them are completely okay. However way you want to think of it, but this one is going to infinity, this one is going to 0. But remember that exponential always goes to 0 much faster than polynomial. So this one is growing to infinity polynomially. this one is going to 0 exponentially fast in k. So this term will always dominate, this term will always not dominate, and consequently the whole thing will go to 0 if lambda is less than 1. If lambda is equal to 1, or absolute value of lambda is equal to 1, then this term will be equal to 1, but this term is going to go to infinity, and therefore the system will become unstable. Okay, so a raised to k will go to infinity. Does that make sense? Does that help you understand what exactly would happen in these kind of systems in the discrete time system? So what we have done so far in today's class is understood the connection between the eigenvalues of continuous time system and the eigenvalues of discrete time system. How do the two relate? And we've also realized that the modes of the system in diagonalizable case is easy. The modes of the system in the non-diagonalizable case is slightly complicated but not unfathomable. And we've been able to derive what the modes of the system looks like, and based on the modes of the system we are able to figure out when is a raised to k matrix going to infinity versus when is it going to 0. So if absolute value of lambda I is greater than 1, this will go to infinity. If absolute value is less than 1, this will go to 0. If absolute value is less than 1, it's going to go to 0. If absolute value is equal to 1 or greater than 1, this is going to go to infinity. For the more general case, your lambda matrix will have multiple Jordan blocks, and then you can come up with the expression for each of the Jordan blocks, and that will give you the modes of the system. So that expression is more complicated. Understanding is easy. Once you know these two different forms, then all you have to do is stack everything together in a matrix format and things will work out. So I'm not covering the more general case of the Jordan form. Any questions so far? Okay. So if a continuous time system is stable, you discretize it. The discrete time system will also be stable. If the continuous time system is unstable, you discretize it. The discrete time system will also be unstable. What is an example of an unstable system? I mean, I know you have seen the battery thermal runoff, but if you think about detonation, the bomb detonation or nuclear detonation, all of those are unstable systems because the states go to infinity very quickly. But actually, the states go to infinity exponentially fast, and that's why it's a explosion. On the other hand, yeah, I think you get the idea. Like you've seen enough number of unstable systems now in assignments that you understand under what conditions would the system be stable and unstable, and what does that mean in real world setting. Okay. The next topic is stability, but turns out that stability and modes of the system are related. And we've already talked about what stability means in the context of linear system, in the context of discrete time system. So if you're, how about I give you the definitions of stability and then sort of comment on it. So let me write down this particular case. So this is non-diagonalizable. And a raised to k